Hello students, welcome to chapter number 1, Gravitation from Science and Technology. In this chapter we are going to focus on 7 topics: gravitation, circular motion and centripetal force, Keplers laws, Newton's universal law of gravitation, Earth's gravitational acceleration, what is the difference between mass and weight, and what is free fall in any kind of gravitational environment. Now, as you all have learned that gravity or gravitational force acts between two objects wherever they are in the universe. Now, the first point that we need to understand is that Earth attracts all objects towards itself, and this attractive force is at the center of the Earth. We'll look at an example to see how this is true. So let's say that this is our Earth and you are standing on this side and your friend is standing on this side. This is my center of the Earth, and you and your friend both are along the center line. Now what we want to do is both of the friends, that means you and your friend, have to jump along the center opposite from the center of the Earth. So I'll call this person A, I'll call this person B. Person A is going to jump in this direction and person B is going to jump in this direction. So if let's imagine this particular scenario. If A jumps, what will happen? So when you start jumping, you lift off from the ground, you go up, and then there comes a certain point where you stop and you do not go furthermore in the up direction. Instead you start falling down back from where you started. Now as this happens with A, this is also going to happen with B. No matter where you stand on the Earth, this is always going to happen. So now if this happens, that means there is something common that is going on. So what are the common things? The first common thing is that both are being pulled down. Both are being pulled down. This means that the Earth's gravitational force is clearly stronger than your own gravitational force, which is why you are being pulled towards the Earth. Now, second thing that is common is that both A and B are being pulled towards the center. Now, if you think that this might be wrong, let's take a third example. Let's say that there is a person C standing here and he also tries to jump. What is going to happen? Now, like, this is the line along the center. He also, if he jumps straight up, he will come down eventually. Now, the thing is that he's jumping along a straight line and he comes along the straight line. So that straight line, when aligned with the center, shows us that the person who is jumping is pulled towards the center of the Earth. That means the gravitational force is towards the center of the Earth. So as we can see, Earth attracts all objects towards itself, and this attractive force is at the center of the Earth. So as we took an example, if we have a friend in Japan who is jumping in Japan, and if I am jumping here in Nagpur, both will be attracted towards the center of the Earth. Now, the force on an object is towards the center of the Earth along the perpendicular from the position of the object to the surface of the Earth. Now we are going to write this particular concept in our presentation, and we'll see how this is going to happen. So the force of an object is towards the center of the earth. Remember, this was our first condition that we could find common between A and B in our previous example. So here I have an earth. Let's say I have a person. The person A shifted to this point, so he's standing here now, and the person B shifted to this point. So this was my first derivation from that example. And the second is, this happens along the perpendicular from the position of the object. Now, this particular derivation is given on your textbook page number 1. You can see second paragraph just next to the figure 1.1. In the very first paragraph next to figure 1.1, the second line, the force on an apple on a tree is towards the center of the earth along perpendicular from the position of the apple to the surface of the earth. Instead of apple, here I am going to generalize and say that every object is pulled towards the center of the earth. Now, the one thing that here we need to understand is, what is this particular sentence? This happens along the perpendicular from the position of the object. So, let's take the case of A. I'm going to draw a very small picture in which we can see only A and nothing else. So, here we have A. A is standing on this side, and we have to imagine a tangent to the surface of the earth. Now, if I extend this line, so I can safely say that this is 90 degrees where A is standing with respect to the surface of the earth. As we can see in our statement, this happens along the perpendicular from the position of the object. As we can see, the angle between the object and the earth, that means this particular angle is 90 degrees. Therefore, this always happens along the perpendicular. Now, similarly, if I take the case of B, I have a tangent here. Again, I extend the line for B. This angle again is 90 degrees. This again is 90 degrees. And it does not matter where you stand on the earth, the force that acts on the object who is on the surface of the earth is always going to be along the perpendicular from its position on the earth. So let's say if a third person was standing here, let's say this is C, so this is the third position, this is C, this is my extended line towards the center of the earth, and this is my tangent. This again is 90 degrees, and therefore it does not matter where you stand on the earth, the force always is going to act along the perpendicular from the position of the object. Now, moving to our third point, force and motion. A force is required to change the current state of motion of an object. So let's take an example and understand what this particular point means. A force is required to change the current motion. Now, let's say your mother is cleaning the house and she wants to clean under the dining table. So she wants the chairs moved. So initially the chairs are at a rest position. Now you pick the chair up. That means the person is applying a force in picking the chair, and now he's moving the chair to another place. So there are two particular cases here. The first case is when the chair is at rest. Chair is at rest. So its current state is rest. Then you come along and a force is applied. Force applied. Now the current state changes to constant motion, because you're going to take the chair to another room or another place with some speed, right? So this is a constant motion that happens. So now the current state has changed from resting to a constant motion, and a force was required to do this. So this is what we need to understand, that a force is necessary to change the motion or current state of motion of any object. Now let's take the second case. Now remember, our current state was constant motion and we did not keep the chair at rest. So in the second case, my current state is constant motion. And now I reach at my destination where I want to keep the chair. So again, now I'm going to remove the force. So remember, first I applied the force, then I removed the force. That means instead of putting force, I am removing. So the force is removed, which means gravity will act and pull the chair down. So as we learned that gravity pulls everything towards the earth. So gravity acts and now the current state becomes resting position. So again, in the second case, the moment a new force acted, the current constant motion initially changed to resting motion finally. This is what is important. So as we apply a force, it changes the current motion of an object. Now there is one thing that we need to note, that force also changes the direction of the motion. Now if let's say we can take an example that let's say you are walking in the rain and the rain is falling perpendicular to the surface of the earth. Now what this means is that we'll see from a diagram that rain is falling in this way, in this way, in this way, in this way, and then suddenly wind starts blowing in this direction. Now we are going to draw this in our second diagram. So what happens to the rain droplets is, instead of falling like this, they start falling in this direction. You all must have realized this, that the rain is coming towards you, or if the wind is blowing, then the rain is coming from the direction in which the wind is blowing. So this is what happens, that force when applied from a certain direction can also change the direction of the object. Now moving on to circular motion and centripetal force. The first point that we absolutely need to understand is that centripetal force acts on an object that is in a circular motion. Now we'll take an example and see. Now remember the statement, you can check this statement from textbook page number 2, that I'll mention this to you. So, under the topic circular motion and centripetal force, you can look at paragraph number 2. It is 4th line from the end of 2nd paragraph. A force acts on any object moving along a circle and it is directed towards the center of the circle. So we are going to see an example. All of you have heard about hurricanes, cyclones and tornadoes. Now in this case we are going to look at the top view of a hurricane, cyclone or a tornado. So this is just a rough diagram. So it goes like this, then it goes like this, and it keeps going inside. And then here there is a particular center. So I can roughly say that this particular diagram, or the top view of a hurricane, looks like a circle. So let's say we have an object here. I have an object O here. What is going to happen as time passes by? Now this is going to be the second position. This is my first. This is second. This is going to be the third. This is going to be the fourth, and so on. As we keep going, at some point this object is going to reach inside of this particular hurricane, cyclone, or tornado, whatever you want to call it. So what is happening here is that no object moves or starts moving or starts motion by itself. There has to be some kind of force. As we learned in our presentation, that as in this slide we can see, a force is required to change the current state of motion of an object. So in this case, as we can see, when the object starts its at rest, then suddenly a force starts pulling it towards the center of this particular hurricane. As it starts getting pulled, it is moving towards the center. So any object that moves along a circle, it is directed towards the center of the circle. Now in this particular case, this is not exactly a circle, this is a spiral, but as we can see that the object is moving towards the center of the circle. So if I have a circle and an object is here, then there is always a force that acts in this direction, which is along the center of the circle. And this particular force is called as centripetal force. Centripetal force. Now, observing this, we can clearly see that any object on the outer edge of the hurricane is getting pulled towards the center. This means that there is a force acting upon the object moving in a circular motion. This force of an object which is directed towards the center of the circle is called a centripetal force. Now note, centripetal means center seeking or trying to go to the center. So the definition of centripetal is trying to go to the center. Now, as we know that moon travels around the earth in a definite orbit, during which the moon's speed and direction constantly changes. Now, similar to earth, moon also orbits around the earth. So if I say that this is earth, then moon constantly orbits around the earth. I'm going to call this as moon. This is moon and this is earth. Now, we know that moon constantly orbits the earth. There is no point in time that you will have, or you will see a day that moon is just sitting at one place. That means moon is being acted by some kind of invisible force which we cannot see, because we do not see like anybody holding a string to the moon and rotating it around the earth. That means there is some kind of invisible force that is pulling moon towards the earth, and so the moon is rotating around the earth, or you can say orbiting around the earth on a constant basis. So this invisible force is applied by the earth's gravitational force. This invisible force is applied by the earth's gravitational force, which keeps the moon in a constant orbit. And as the moon orbits the earth, similarly in our solar system, all the other planets orbit around the sun, because sun being greater in size keeps all the planets attracted towards itself, and therefore all the planets orbit around the sun. Now, as we know that all the planets orbit around the sun, Kepler, being a scientist, he observed this and he developed 3 laws. So we're going to see what these Kepler's laws are. So planets in our solar system revolve around the sun in an elliptical orbit rather than a circular orbit. Now here an important concept is elliptical orbit. So as we all know that this is approximately a circle, and a circle has one center. What an ellipse is it takes circular parts and it is extended in this way, and an ellipse has two centers instead of one. So planets orbit around the sun in a elliptical orbit rather than a circular orbit. Now, ellipse is a geometrical shape that is obtained when we cut a cone at an incline. You can see this from a textbook page number 3 under the do you know topic or headline, and you can see there is a small diagram at the center of the pink box, and you can see how the ellipse can be formed. A circle has only one center, whereas an ellipse has two centers known as focal points. Now, the three Kepler's laws. Law number 1. The orbit of a planet is an ellipse with the sun at one of the foci. Now we're going to see how this happens and how Kepler came to this particular conclusion that orbit of a planet is an ellipse with sun at one of the foci. So before we start this, first we'll take an activity. Let's say that I want to cook something, and suddenly I turn the gas on, and I want to check if the gas is on or not. So let's say I'm right next to my gas and I keep my hand over the flame. So what happens if I keep my hand just over the flame? After 4 or 5 seconds, my hand starts to warm up or even burn. That means I am feeling the heat. That means I can feel that my hand or the temperature around my hand is getting higher and higher, which is why my hand is burning. Now in the same case, let's say that I want to check if the flame is up or not from a distance of 10 feet. So I am standing 10 feet away from the flame, and from my place I try to feel the heat of the flame on my gas. Do anybody of you feel the flame? At least I do not feel any flame. That means if I am far away from the flame, my temperature does not rise, which means I am kind of cold when I am very far away. So let's see what happens in the case of Earth. So this is my elliptical orbit of Earth. This is one center, this is my second center, and we are going to assume that sun is at this particular center. So now we are going to see two cases. One when the Earth is here, and the other when the Earth is here. Now we know that we have 3 seasons: summer, rainy season and winter season. For now we are going to skip the autumn season, or we are going to skip the spring season. All we need to focus on 2 seasons. One is summer and one is winter. So when it is summer, the temperature is very high. As we know, the temperature goes to 47, 48, whatever it is, it does not matter. What matters is that we start feeling the heat. Now, as we learned from our previous activity, if we go near the flame, our temperature starts to rise. So if I am on Earth and the temperature is rising, that means I am very close to the sun. So that means this particular distance is during the summer. So this particular distance is during the summer. Now, as we have understood in our previous activity, if I am far away from the flame, I do not feel the heat. Or let's take a better example. If my hand is above the flame and I move my hand a little bit up, I suddenly start feeling less warm. Then let's move it a little bit more up. Then again, I suddenly start feeling even lesser warmer. Then if I keep doing this, there will come a point where I do not feel the heat at all. So that is what happens when Earth is the farthest away from the sun, and this duration happens during the winter. That means the Earth has 2 different distances during its orbiting around the sun. But if we take an example of a circle, so let's take an example of a circle. If this is a circle and this is my center, and sun is at the center, that means at any point of its orbiting, Earth is going to be at equal distance from the sun, because in a circle the radius is always equal. In a circle the radius never changes. So if the radius never changes, that means I should feel the same amount of heat every time. And what that means is that I should have only one season throughout the year. But as we know that Earth does not have same season every year. It has a summer season, it has a winter season, which means the Earth's distance varies from the sun from time to time, which means that the Earth follows an elliptical orbit around the sun. Kepler's second law states that the line joining the planet and the sun sweep equal areas in equal intervals of time. So if this is my ellipse, that means the orbit of Earth around the sun, and this is my sun, then the Earth sweeps equal amounts of area from the points joining the sun and the Earth, from the line joining the sun and the Earth. So if Earth is here, this is the second position. As we can see, as the distance increases, the area gets narrower, but the value of area does not change. That means if this point is A, this is B, this is C, this is D, and this is S, then CSD is equals to BSA. Now remember, both these values are in terms of areas. This is not distance, this is area. So the Earth sweeps equal amounts of areas in equal amounts of time. Now there is no particular reason as of yet to understand why this happens, but in the next section we'll be seeing how Newton comes to the conclusion that why this happens. Now moving on to our last Kepler law. Kepler's last law states that the square of its period of revolution around the sun is directly proportional to the cube of the mean distance of a planet from the sun. This means that the amount of time a planet takes to rotate or revolve around the sun, its square. So let's say that Earth takes time t to rotate around the sun, so that t and the square of this value is directly proportional to the cube of the mean distance of a planet from the sun. Mean distance of a planet means we're going to say that mean distance of a planet from the sun is r, and this value's cube is directly proportional to the time it takes to revolve around the sun. Now in the next section we'll be learning universal law of gravitation, and we'll understand how Newton came up with conclusions from Kepler's laws and how these two confirm each other's theories. This section will end here. Thank you.